What we did before was to define the likelihood, or at least set it in the Poisson data regime. And we played a bit with using some tools to load data and vary parameters and evaluate the likelihood at different values of those parameters. Actually, let me just quickly show you. So what we can also do is we can vary the normalization parameter in a grid from, let's say, 10 to the minus 5 to 5 times 10 to the minus 5 with 10 steps. Make a nice little loop there. And then we vary also the photon index. We assign it values between -1 and +1 with 10 steps. And then we're just going to print out -1/2 times this Wstat to get the log likelihood of that particular parameter set. Then I'm just going to make another print here. So it's going to make a grid over these and evaluate the likelihood there. And what we get then is this. And you see how the log of the likelihood varies over photon index and normalization. And yeah, you probably want to maximize the likelihood, but you already can imagine some of the problems that are interesting here. So we want to, I left with this slide, we want to find regions with high probability mass, so where the volume and the density of the posterior is maximized. This is where most of the probability is concentrated. This probability mass we want to identify. And for that, we use some parameter exploration algorithms, parameter space exploration. So here we go, parameter space exploration algorithms. This is one of my favorite things to think about. And let's think about what we need here. So very often you will see these kind of corner plots which show segments or pairs of parameters and projections of this probability distributions here in contours. And what we often encounter in astronomy is that they are not nice Gaussians, but they have maybe multiple solutions. They have these kind of banana shapes, and they also can have quite a few dimensions. And so we need algorithms that try to reconstruct this. And the first class of algorithms is just to use optimization algorithms. So you just try to find the peak of this, for example, with simplex minimization. Another type of algorithm, which I include here in the category of local sampling, is Markov chain Monte Carlo. And this is a very popular algorithm that you'll often encounter in astronomy. And I would recommend that you try to implement MCMC by yourself to play with it a bit and understand it. But basically what happens, I will explain how that works. Then there are algorithms that don't just find a local maximum, but a global maximum. I will not be able to cover those. And then there are algorithms that can sample from this global parameter space and represent also in case of multiple solutions and complex degeneracies, can describe these weird shapes accurately. But let's start in the beginning. I don't know if this was covered before, but I think it's important to repeat. If you find a best fit, which means maximizing the likelihood, that's just an estimator of what might be a good value. But often then you want to understand the uncertainty, so the parameter range. And the confidence intervals are constructed in the following way. You assume, let's say, you found a best fit of your parameter mu of 0. And then you think, well, what happens if I generate a lot of data under this, assuming this is the true value. And then if you go in your log likelihood, a value of -1 down, you can define a range. And that range contains the best fit in 68% of the data realizations. So if you generated different data sets, assuming this true value, assuming this best fit that you actually got with your real data was the true value out there in the universe, if you generated all these data sets, then this fit procedure would land within these intervals. And this works if the best fit is away from the boundary, if the model is linear, and if that best fit parameter is actually the true parameter out there. But then you have to ask yourself, well, was this actually the question you wanted to ask? You're not maybe so interested in how good your fitting procedure works and what's the behavior of the simplex best fit. But you want to actually know what could be the parameters out there, right? You're not interested in how your likelihood changes, but what the parameters are. And so if these conditions, also if those conditions are not met, then these confidence intervals, you cannot construct them analytically, like I just showed before, and you have to simulate actual data sets. It's called parametric bootstrap, and then you can calibrate this confidence interval to quantify how well you can recover the actual input value. So here you'd have a true input value that you put in your simulation, and then you have your output of your estimation. And one particular case here is detection. So if you have some parameter, for example, the normalization of a new component, you want to say, okay, I detect this, I don't know, emission line or something like that. Then that normalization will go off from 0 and become positive. But how is that significant? So in this case, you would simulate without that extra component, and you would derive new normalizations by fitting that extra parameters, and you would get a distribution out. And then you could say, well, if my parameter estimated is never reaching a value beyond something, or in 99% of the cases it doesn't reach above some value, then you could say, well, if in the real data set it went beyond that, then you have confidence that there is actually something more in the data, because you simulated without that component, but now it seems to be going beyond that null model. From best fits, what's pretty common, unfortunately, is to make histograms of best fits. So here I illustrate that. You can imagine for each data set, you find your best fit, but of course each of those has some likelihood attached to it. Maybe some data sets are uncertain, so you have a wide distribution, some are less certain. And basically what you have with these histograms of best fits is that you have a convolution of the true parameter distribution with the measurement error and the scatter of your fitting parameter. And so you're not really measuring the true parameter distribution, but some convolution, and this is even more problematic if you have asymmetric. So if you have, for example, upper limits sometimes, or if you have a lower bound on these parameters. And the clean solution to these are hierarchical Bayesian models, but this would go too far now. So going beyond confidence intervals and best fits, we come to the topic of sampling. So we already know that the posterior is the likelihood times a prior, and we want to identify regions with high probability. And we can represent probability distributions like this with a bunch of samples. And where they are denser, we would say they have higher probability. And where they are less dense, we would say they have it represents a low probability. So we can represent distributions with samples. You could also use a grid. That's another way, and encode the probability or the likelihood for each grid value. Now, if you chose a grid like I just demonstrated to you earlier, then you can evaluate the likelihood in each of those grid points, and you can compute the relative importance. So that they all normalize to 1, and then you could choose the one or choose the region that gives 90% of that likelihood. And by the way, the evidence then, it's just the sum of all these likelihoods. Now you immediately recognize that it matters how you define your grid, if you define it in your parameter value or in the log of that parameter value, right? Because your spacing will be different. And the likelihood alone doesn't tell you how to space this. And this choice of spacing, this how you define what is equal volume, that's essentially the prior. So for the Bayesian analysis, you would not use confidence intervals, but credible intervals, which define where most of your probability density is. So for example, you would say, well, between here and there, that's my interval that contains 90% of the probability. And there are a couple of definitions of how to construct these. Now, if you have two models, what you can do is the same as in parameter estimation, where we said, well, we're going to pick the grid points which contain most of the likelihood. Now we could say, well, is most of the likelihood here or most of the likelihood here? And you either pick model 1 or model 2. For example, if model 2 contains 99% of the likelihood, or the evidence in this case, because you summed over it, then you would pick that model, right? And immediately you see that it depends how many grid points or what prior you define inside the model, but also across the model. So how that volume is sized relative to that volume. And these are model priors. Okay, I think I said most of this. So identifying either the region of the parameter space that contains most of the probability or the model that contains most of the probability. Now, grids are nice conceptually, but they quickly become infeasible because you can't slice your parameter space very nicely if you have more than a few parameters. And so techniques were developed to avoid this, and some of them are mentioned here: importance sampling, MCMC, and nested sampling, and I'll go into details in that. And the difference here is, instead of using a grid, you use samples. So you have a bunch of values, perhaps with weights, that represent your probability distribution. And each of those values in those chains or in this posterior sample is one solution, and they are equally probable solutions to your problem. And you should use these as a probability distribution. How can you use them? Well, you can make histograms to recover the distribution. You can make quantiles of these, so you can sort them. You can find 10 and 90% quantiles. Then you have the credible intervals. You can take each of those values, you apply it to your model or compute something else. Then again, you get a chain of values out. And so you can make some further computations propagating that uncertainty. You see a model plotted with the uncertainties. And here you see posterior values of luminosity that were derived from parameter values. So here I used fluxes and redshifts and computed luminosities and redshift. So let's get into Markov chain Monte Carlo. I will cover this because it's quite common, and I think important to understand also when you referee papers or read papers, that you know what it is. And it's a useful technique in many cases. So the idea of Markov chain Monte Carlo is that you choose a starting point, and then you do the following forever. You have a proposal distribution, for example, a normal distribution in your parameter space. You jump somewhere, and then with the probability, so with the posterior probability ratio of the new point to the current point, you accept. You accept in particular, if the probability increased, you always accept. And if it decreased, you accept with a random number between 0 and 1. And if you do accept, so the lower the probability, the less likely you will accept. And then you have a new point, either the current point or the chosen point, and you add that to the chain. So it can have repetitions if you didn't accept. And so basically you're jumping around. You have this kind of transition kernel to go from one position to the other in a parameter space, and you build up a chain of points. And this chain of points will have, in the end, the probability distribution of your posterior. If you run this kind of procedure on a flat probability distribution, then your chain will have kind of this, here they all started from the same starting point. They will have this kind of random walk behavior, and they will explore the space in a sort of correlated random walk. There are a couple of ways to define these proposals. One is Metropolis Hastings. Goodman-Weir is a pretty popular example, and more advanced algorithms use Hamiltonian Monte Carlo. The advantages, well, of Metropolis Hastings is it's relatively simple to implement, but it has a lot of difficulties getting to very different or very far regions of the parameter space. So the mixing of this is relatively poor. This ensemble Goodman-Weir proposal is very good for Gaussian likelihoods, but if you have kind of banana contours that you're trying to explore or high dimensional problems, then this tends to collapse and not be reliable. For high dimensional parameter spaces, Hamiltonian Monte Carlo is very good, but you need gradients in this case. So you need the derivatives of the likelihood, which is often not available because you can't differentiate the models. So if you start your chain, what often happens is if you have most of your probability in this banana, for example, it will walk towards that banana, and then it will walk around on that banana in a sort of random walk fashion. And then you can plot your particular parameter value versus iteration of that chain. You should care about the convergence of this, that it really traced out everything. And there's a lot of literature on how to test if you ran your chain long enough that it really represents your chain. And this is not so easy, and one of the reasons I prefer nested sampling, because you have to take quite a lot of care on these convergence tests. Another difficulty of Markov chains is that they can get stuck if you have a likelihood with multiple modes. It can get stuck in one particular mode. So for example, if you start your chain, let's say here, then it will walk up here, but it will never go down in likelihood, or the probability that it will jump down to very low likelihoods is very small, so it will just explore this peak forever. And there are some techniques to avoid this, which I will not go into detail. One is to dampen this likelihood. That's called tempering or annealing, and then explore on this, and then mix various temperatures of this likelihood. Okay, so now we could use MCMC or various other algorithms to explore likelihoods and get posterior distributions. Let me briefly touch on model comparison as well. So in this case, remember that we are trying to estimate the integral over the likelihood over the entire prior space. And that cannot be achieved with a Markov chain Monte Carlo. But you could do, for example, a grid in principle and sum up the likelihoods over that. But that's, of course, not very efficient. But well, let me back up for a little bit. Different ways of doing model comparison. Of course, this based on the evidence is not the only one. And you should not use Bayesian model comparison if you don't have priors that are well justified. So if you have just empirical models like polynomials or something, you probably wouldn't use Bayesian model comparison because your priors don't make any sense. So if you have empirical models, what you can do is you can judge whether they encode all of the information that your data have. These are some information-based criteria that you could use. One of the famous ones is Archaic Information Criterion, AIC. You can also evaluate models based on their prediction quality, and this is very popular in machine learning. So you leave out some of the data, for example, you train or fit your model based on some test data, some training data, and then you evaluate its prediction quality on the holdout data, on the test data. You will hear more about that later. So that's one way to judge empirical models. I'll not go into detail here, but if you have multiple components and you want to test whether this component is there, maybe you want to you want to set a limit based on, I mean, you can always hide some component with very low normalization. So you might want to define some region where it actually matters that that component is there. So this is one way to define probability distributions or the significance of a probability distribution to lie outside that zero range. But I will mostly talk about Bayesian model comparison. And this can often be the case in X-ray spectral analysis that your priors are actually well justified because we have physical motivations for different models, for example, absorption in AGN or things like that. So the information criteria that I mentioned earlier, this information criteria, Archaic Information Criterion, AIC, basically asks, is a more complex model worth storing? And for that, you have to basically judge the number of parameters that you're using to describe or compress the data or describe the data in your model and how well it fits the data. So what it does is it takes 2 times the number of dimensions and it subtracts 2 times the maximum log likelihood. And in case of Wstat, it's even simpler. And actually, this looks very simple to then just choose the AIC with the lowest number here. But actually, it's derived from relatively deep roots in information theory. And it's sort of nice because it's independent of priors as well. But of course, you don't have any uncertainties here on the estimate to judge how, like if you're 0.1 higher in AIC, is this really significant or does it really mean something? But I would recommend this for empirical models. I already talked a bit about Bayesian model comparison. So you compute the evidence for 2 models, and then you basically take the ratio of these evidences. And the idea then of these Bayes factors, that's what they're called, is that it gives you, if the models are equally probable a priori, that it tells you the probability of model 1 compared to probability of model 2. And the way that works is really interesting because it doesn't use the number of parameters of these two models. Instead, it sort of punishes how diverse the predictions are. Let me explain that a bit. So let's say you have one model, model 2, which is relatively inflexible. So it can only produce certain shapes. And so here the data fit not so well, here the data fit sort of, and here the data fit not so well either, but it doesn't vary a lot over this parameter space. So the likelihood is sort of medium, and you have not so much variation over this space. Now let's say you have another model. This could be, for example, a high dimensional high order polynomial, let's say, for example. So it's let's say this is a very flexible model that can produce all kinds of data sets. So up here you produce this shape, down here you make these kind of wiggles. So this can describe all kinds of data. So in the best fit, your likelihood is very high because it perfectly traces out the data. But because as you walk along in this parameter space, you can produce all these kind of shapes. Most of these shapes don't describe the data. So the volume that actually describes your data is very tiny as compared to the entire space. Whereas here, because it varies so slowly and because it produces so few shapes, the volume is substantially larger. And so what you have then is, if you multiply this likelihood and volume together to get the integral, is that here you have a very good fit, but the volume is tiny, which punishes this model. So the evidence for this model would be quite low. Whereas this relatively simple model, which doesn't produce so many data sets, would get the preference, because likelihood and volume are both sort of high. So this is how Bayesian model comparison punishes diversity in prediction, and that's sort of a nice concept. Yes, so I talked about the ratio in these evidence values. That's the base factor. You have to multiply this by the prior odds of model 1 to model 2, and then you have the posterior odds, which is what you're actually interested in. How probable is model 1 given the data compared to model 2 given the data? Right, so yeah, this is the case if you have more than 2 models. What I would recommend is that you compute just the base factors and leave the model priors then for the discussion. So basically you say, okay, the base factor is this, and if we assume it's equally probable, then you have these posterior odds. But if you prefer model 1 much more, then even maybe the base factor is still extremely high, and then you can still discuss that. So I would leave the model priors to the reader, or motivated by theory maybe. The other thing I want to point out is, just because model 1 is model 1 to model 2 has a 3-to-1 ratio of odds, does not necessarily mean that model 2 is correct in this ratio of cases, right? So this doesn't necessarily correspond to false selection probability. So how often you would wrongly choose your model. For that, I would recommend simulating data sets again. Maybe no, I didn't have a slide on this. So for example, if you want to know how often you would falsely select model 2, I would simulate data under model 1, compute this prior odds, and then you get a distribution of posterior odds. You get a distribution of posterior odds or base factors. And then you can say, okay, well, if it goes way beyond this value, then you would choose model 2, and then you have also false selection rates. Okay, let me come to algorithms, in particular one algorithm to compute these integrals over the entire parameter space, also in high dimensional and complicated spaces, and where grids are not sufficient, which is basically all of practical cases. And for that, I want to explain nested sampling. So nested sampling is also a Monte Carlo technique, so it's based on random numbers. And the difference here of nested sampling and Markov chain Monte Carlo is, in Markov chain Monte Carlo, you basically jump in your parameter space and you explore up and down your likelihood function or your posterior target distribution. And so you have these kind of vertical slices where you sample and probe your probability distribution. So the integration is sort of vertical here. In nested sampling, we try to estimate the width of sort of horizontal slabs of the posterior distribution. And if you make slabs like this, you can compute the total integral over this probability distribution as the height times the width of these slabs. So you basically take a sum and you compute the likelihood times how much smaller the upper slab is than the previous slab. And you basically make these kind of pyramids. And how does this algorithm work? Okay, so you start with your entire prior volume. Let's say this is a 2D box in this case. You randomly throw in 200 points in this volume. And now you remove one of these points, the one with the lowest likelihood. And if you imagine that, then you can convince yourself that the volume represented by these points, if you a priori say they all have equal weight, now you remove one, you've reduced the volume represented here by 1 over the number of points. And so if you imagine them sorted by their likelihood in particular, you take out the most extreme one, you've reduced the volume by a certain amount. And now we can repeat that procedure. And now we shouldn't sample in this region that we already excluded. So we have to require that the new point has to have a likelihood higher than the one we just threw out. So we sample a new point from the entire prior volume, but we don't accept the ones with lower likelihood. And now we're back to having 200 points. And we can cut again the one with the lowest likelihood and so on and so on. And it iterates to higher likelihood thresholds and to smaller and smaller regions correspondingly, because we only ever put points in regions that have a likelihood above some threshold. It takes advantage here that the points can be ordered by their likelihood, but you need an algorithm which efficiently draws new points uniformly distributed across the volume, so according to the prior, but with a higher likelihood than the current threshold. So you're basically scanning up vertically, and at some point you are left with a tiny volume that you're sampling, where all points basically have the same likelihood, and you are essentially done because the volume is so small that it doesn't contribute to the integral anymore. So keep in mind here, we know now the width of this slab at each iteration, because we keep track in each iteration, we slice off 1 over 200 of it. So we can keep track of how quickly this, this volume that we're sampling shrinks. And we know the height of each slab because we know the likelihood threshold at each iteration that we are removing. And that gives you the estimate of this evidence. And it gives you at the same time, if you give each of those points a weight based on this, you also are sampling the posterior distribution. So it gives you everything MCMC gives you. It gives you a posterior chain, and it gives you the evidence integral. So you can do parameter estimation and you can do model comparison with this particular algorithm. For MCMC, what you have to use is some transition kernel to complete the algorithm, to make it jump and generate new points. For nested sampling, similarly, you have to insert an algorithm which replaces the current point with one that is sampled uniformly from the prior, but higher, with a better fit than the one you just removed. And there are a bunch of solutions to that. Here there are some listed. I will not go into detail except for one of them. So basically, RadFriends is the algorithm implemented in UltraNest, which is what BXA uses at the moment. Multinest is what it used to use, but the method is very similar. So you already have points that are above your likelihood threshold. The contour is illustrating the current threshold, but of course you don't know the contour analytically. You don't know how to sample directly. So what these algorithms do is they cluster the points into some ellipsoid, for example, and then they, instead of sampling from the entire region, they just sample from the neighborhood of these points. And that's much more efficient to do. Let me just show you an animation of this. So I think it's going to be useful. Yes, so here you see a bunch of points thrown into a parameter space. You see in contours the target distribution that we're trying to represent, and each of the points has sort of a region around it, which defines the neighborhood. All of the green is the neighborhood over which we are currently sampling. You see it's wider than the points because there is sparsity, but it doesn't sample out here. And so this is much more efficient than if we sample from the entire space. And at each iteration, it replaces the worst point with a new point, assigns a weight, and here you see posterior distributions of this algorithm. And you can play with this and convince yourself that this actually also works nicely if you have multiple modes, and it can nicely explore these. Okay, I covered this already. So I said a few words here already. If you want to distinguish models, you probably want to quantify how often you're wrong about your decision. And for that, I recommend making simulations. Here's an example. I'll not go into detail here. But if you generate data under one model and then quantify with whatever method you define to choose between two models, you can measure this false decision rate as a function of some threshold typically that you choose. That's shown here. That's the false decision rate. And so what you're essentially doing in that moment is you're giving frequentist properties to Bayesian methods. So frequentist inference always describes how methods or procedures perform. It quantifies procedures, whereas Bayesian inference quantifies well, the parameters of the model. So it quantifies things that we're actually interested in, not the methods themselves. But if you then make simulations and you calibrate and measure how well these Bayesian methods work in practice, then you have the best of both worlds, because you now can make decisions and define how reliable making these decisions are. And typically using these Bayesian methods, rather than, for example, best fit or likelihood ratios or something like that, they actually perform better in these frequentist properties, such as false decision rates, because they use also the prior information. Here's some practical advice on model comparison, which method to choose when. So first of all, you want to maybe say, maybe you don't have actually two competing models. Maybe you want to say, is this model a good one? And so this is sort of what people refer to when they talk about goodness of fit, which I think is not so well defined mathematically. But if you want to do that, there are a couple of methods to do it. Posterior predictive checks and parametric bootstrap, so where you generate new data sets, are some of the important ones. If you compare different models, I think it makes a difference if you compare empirical models that just try to describe the data without much physics. In that case, I would recommend AIC or sort of cross-validation techniques. But if you have competing physical models, then again, it makes a difference whether you have these kind of additive components in which you can use some specialized techniques, or in both cases, you can do a Bayesian model comparison. Okay, I will take a moment here and ask for questions. So please go ahead and ask your questions.
I have a question about the nested sampling.
Mm-hmm.
So I think you said it was a global sampler. So
Mm-hmm.
does that mean it does not suffer from being stuck in local minima?
Yes, that's correct. Maybe I can show this here.
Because I could imagine, yeah, for example, with this animation, if there was another maximum somewhere else, but the points get all drawn to this local maximum in the middle, right?
Right, so here you see an example with 3 maxima, and then you can see what's going to happen. Keep in mind the green is the region it samples from. So of course, if you have like very, very few points and you have a peak that is extremely narrow, you're not going to find it, but you're probably never going to find it with any method if it's narrow enough. But you see here that the points start to go into all of the minima. I mean, of course, proportional to their volume in the space. And it does trace out all of them.
I see. Yep. Thank you.
More questions, please?
So another question maybe about the comparison of this with MCMC. So I mean, MCMC suffers from local minima more, I guess, but how do both algorithms scale with dimensionality? Because I maybe imagine this one being a lot more expensive when you have a very high dimension, because then you need to maybe start with a lot of points.
Mm-hmm. Yes, so it's complicated to answer in general. It really depends on your problem. In extremely high dimensions, so if you have, let's say, 1,000 parameters or tens of thousands of parameters, then this is hopeless. And most MCMC algorithms are also hopeless, and you really have to go to Hamiltonian Markov chain Monte Carlo. If you have basically nested sampling, how fast it is depends how narrow your posterior is concentrated, because it kind of needs to zoom in to that small volume. And so basically it depends how informative your data are compared to your prior. This is how many iterations it will need. It does scale not so well with dimension, but below, let's say, 50 dimensions, it's performing quite well. With MCMC, it again depends very strongly how the degeneracies are in your parameter space. So if you have, for example, a Gaussian, and you run MC or something like that in, I don't know how many dimensions, then it can converge extremely quickly to that and sample very efficiently. But if you have something that's not Gaussian, it's a banana, or it has heavy tails, or it has, for some reason, it has to explore much more. And so your correlation, your autocorrelations are worse. Then it's quite easy for nested sampling to outperform MCMC, because it's not, I mean, essentially you have to choose the best transition kernel. And if you choose it poorly, then MCMC will perform very poorly. So in general, it's complicated to answer. For low dimensions, especially if you don't know if you just have one maximum, I would definitely recommend nested sampling. For high dimensional cases, the answer is MCMC. But in between, maybe you have to try out and see. The nice thing about nested sampling is at some point it's done. And so you don't have to do these kind of convergence checks that you have to do with MCMC. Are there more questions? Okay. If not, let's see how much time we have left. We have 40 minutes left. I think what I'm gonna do is I'm gonna quickly show you some the example output of the first exercise sheet example with BXA. So this is basically this, just running the script and looking at this output file. So, so we are running this script.
Have you got a question?
Mm-hmm.
Yes, please. Can I ask a question?
Yes, please go ahead.
Hello, this is Haufu. I have a generic question about MC exploration in general. Is there any good method to do a prediction of the sigma so that the code is not going to explore a too large space of the parameter, or not trapped in a too small area?
Mm-hmm. For a Gaussian proposal, you mean?
Yeah.
Yes. So one thing you can do is you run MCMC with some guess, and then you use the samples that you collected, make a covariance matrix or make a standard deviation of that, use that as, and throw everything you had and use that proposal size to start again. And you can have multiple phases like that to optimize your proposal.
Even and to run some trial chains at the beginning.
Yeah. In general, these Gaussian proposals perform very poorly, especially if you increase the dimensionality and if your distribution is not Gaussian.
Okay.
So there are now better proposals, but I think the Gaussian Metropolis Hastings implementation is important. I would recommend all of you to try to implement it. It's just 10 lines of code if you squash it down. And you really learn a lot about how Markov chains can go wrong and how they behave and how to diagnose them.
Thank you very much.
Okay, so let me see how that crashes. So this is a typical output of UltraNest, which is the nested sampling engine that is running inside BXA. And you see each line. Well, let's go to the beginning. Like here, for example, you see for each parameter a line, and between this value and that value, where the live points are distributed. And here for this parameter, they are distributed here. And you can sort of follow along how it narrows down, which kind of gives you an idea where it's running around. And at the end, it gives you, well, the estimate of the log of the evidence. And this value you would use for Bayesian model comparison. So you want to choose the model with the highest of these values, essentially. And here you see the parameter values and their uncertainty. And what I wanted you to try out or look at is in this folder, it produces a bunch of plots, and one of them is a corner plot, or also called pairs plot or diagonal plot. I just didn't like it. Okay, so it looks like this. And so for each parameter, you get a probability distribution, its uncertainties. Here's the normalization. And you see at the moment we are bordering at the lower bound of our prior. I defined the prior just start at 1. Is really smack on the edge here. And that has to do with it's not a good model, but I just want to demonstrate to you this is one way to represent probability distribution by having all these samples and making essentially contours and histograms of these samples. And so this is something you would typically look at. And then you can say, well, if the model is good, you could say, well, the photon index is described by this probability distribution. That's your posterior. Okay. I think I will quickly cover how to deal with backgrounds because I don't want to skip that. And then I will leave it open-end for you to work on the exercises run basically through the demos of BXA and be available for any questions. Are there any more questions right now? Okay, if not, then let me just quickly cover backgrounds because this is something that's very often done incorrectly. And I want you to do better than the typical X-ray astronomer. So backgrounds, essentially the idea is similar as in optical astronomy. You sort of have flat fields that you want to subtract under quotes, and typically when you look at point sources, you extract the spectrum here in blue at the location of your point source with the size of your PSF, point spread function, and you extract the background sort of nearby because the background can vary over the field of view. So you want it nearby, but not covering the source. So you typically have an annulus or something similar, and you get a spectrum that only has the background. So in this region, you have the source and the background, and here you have a sample of just the background. Now we're going to assume that over time and location, it doesn't vary too much where we extracted these. And so you have source counts from source and background spectrum. And now what you can do, okay, this looks a bit scary, but it's not that scary. If you have just the background spectrum and you analyze that, let's say these are your counts in each channel. you again have maybe a response. And if you model the background with the proper model, then you have your physical model here, you project it through your detector response, and you compare it to your data. So this is exactly what I described before. And for this data set down here, your counts down here, you have your background model, which you scale based on the area. And you have your actual astrophysical source model, the one you're actually interested in. You add them together, you convolve them with your response, and then you compare with your data. And you can sum all of these likelihoods together, log likelihoods together, and you can do a joint fit of both of those data sets. You did a joint analysis yesterday as well. This is just formally written out here, the joint fit, summing the C-stats in this case, or the log likelihoods. And this is sort of the conceptually straightforward way. How you would construct these background models is of course not so trivial. So people are often not doing that exactly this way. The other way you can do it is if you, instead of modeling it in the sort of before the instrument, you can also just model it on the detector level, because you're really just doing the comparison here. And if you don't care how exactly that physically arises, you can provide a model in detector channels and then scale that and add it at this stage. So you have your astrophysical model, and then you add it proportionally to the area when you compare to the real observations. That, of course, often requires that your background is well sampled. You have enough counts to really estimate what is the true model here. If the data and the background were both Gaussian, so if you had lots of counts in each detector channel, you could subtract them. And that's what's done in optical astronomy. But because both are Poisson, and typically you don't have more than 100 counts in every single bin, this subtraction is problematic. And so it's better to model both as Poisson. And one thing you can do is you can estimate the rate in each bin independently, and then add this contribution when you in your likelihood. And that's called Wstat in XSpec. The other is to make a model for the background, either in counts or as a physical background model, and fit simultaneously with the source. You can fit the background model first. You can fit the background first, and then translate that background shape onto your source. And this is much easier to do in Sherpa, because it gives you a fit possibility for the background and a fit possibility for the source. But XSpec really tries to hide this detail from you and is sort of misleading. So it even doesn't tell you when it loads the background and the source and you set C-stat, what it exactly does with the background, which is it does an estimate in each bin independently. And this can be problematic if each bin doesn't have a number of counts. And so you really have to be careful how you treat your background. And so please think about that. And the BXA package has some functions available for you to use empirical models for the background. And this helps you not only doing this correctly and unbiased, but also extract more information from the data, because if you know your background well, you have less uncertainty in where the source photons are coming from. Here's an example for eROSITA, the energy spectrum of the background. Essentially, you have a sort of flat background coming from particles. So this is, for example, the solar wind. And then you have a soft dominated background. It's coming from a bunch of components, for example, the hot gas in the local bubble, the halo, and so forth. And then you have also a cosmic X-ray background from unresolved AGN. That's typically a photon index, so the power law with index of minus 1.4. And these AGN are unresolved, and they just fill up the universe, and they contribute also some hard tail here. For some problems, you have to empirically model the background. Here is a new star example, especially if you cannot extract necessarily something close to the source, then you might have to make more physical assumption about the spacecraft position, things like that, to really extrapolate what's going on in your source region. That's also very important for extended sources. Sometimes in clusters, you don't even have a region where there's no source emission. It's all filled by the cluster, galaxy cluster, for example, and you don't have an opportunity to extract a clean background spectrum. So then you have to make more assumptions or be more careful. Yes, so here is another way of doing background models in detector channel space. Here I did a PCA, principal component analysis, which you'll hear about on Monday, how that works. Basically looking at a large number of data sets here from XMM and characterizing how these backgrounds change or what the most important shapes of these backgrounds are. And this is a way to automatically construct models, because now you can mix these components to describe one particular background in one particular source that you're interested in. So this is an automated way to find background descriptions, and this is also available in BXA for you. Okay. Yes. People often are concerned about spectra with very few counts. What happens if you have zero count bins and AGN with 5 counts? What do you do? My opinion here is actually there's nothing special going on, because you have your likelihood. You can, even with 0 count, with a spectrum of 0 counts, you can make these posterior estimates. The uncertainties are just going to be large, and if your algorithm is good, you get posterior distributions out, and there is not really an issue. Here's an example varying. So I simulated a bunch of number of counts, and I generate a new data set with lower and lower normalization, lower and lower flux. And on the right, you see the posterior distribution, in particular here of a power law normalization essentially, and the obscuring column density, so how much material is in the line of sight. And you see the posterior is growing and growing as you get fewer and fewer counts. At some point, you don't know anything anymore, but you do know that it can't be an extremely bright, unobscured source. So even if you have 0 counts, you can still get information out of your spectrum. Okay, I will stop here and first take questions, and then we'll put you in the breakout rooms again. And I will just let you work on the example and play around with BXA as long as you want, and just be available for questions. So if you, let's say, if you are in the breakout rooms and you have questions, either message me or Helen so I can join and help you out. Okay, so any questions at this point? Let's see. Yeah, so I think the example simplest is just a good starting point for the automatic background model and PCA background. You have to run it in the directory of the BXA code. So if you download a copy of the BXA folder, you will also get the Swift directory, which contains the data for those two other examples. So sorry for that, not pointing that out. But if you get started on the simplest script, then you can modify the model there and yeah, try out different models and see what log Z you get and what posterior estimates you get. So for example, you could use let me type something. Yes. Okay, I should probably add that file. So you could define, for example, oh, sorry, this is wrong. So it should be multiply. So we had the first, which is just a power law with the name myPow. And you can multiply on absorber. It's one particular absorber model, TB-abs. And so that would make a photoelectric absorption. So I just joined the group, the room 2. They had active discussion on whether the model is good or not. Would one of you in that group like to share the screen and maybe talk a little bit what you thought of the model? There was William and Luca and...
Hi, I can share my screen, just that we're still trying to figure out what all the plots were, but I apologize, I've got a lot of windows open, so it's a bit messy. Where's that? Right, so we're just trying to figure out really what all the plots were. So we suspect that this one shows the black line as the model and then the red points are the data.
Yes.
And you can see that it's not a great fit. And then we went to the corner plot, which I think is this one. And as you said earlier, you placed the prior on. So if you look at the code, which I pulled up and was just about to change to see what happened. Line 17, line 17 in example simplest had the prior defined as 1 to 3 on the photon index. And so you can see that, in the in this plot, because we've got the prior defined in the wrong region, all of our values are right up against this lower value. So it's difficult to assess, I guess, whether this model is a good one, because we're not fitting the right parameter space, if that makes sense.
Yes.
Is that broadly correct? Or?
Yes, yes. So if you show the convolved model plot again, so this is in PyXspec, just so people are not confused. For PyXspec, BXA also makes some nice plots for sure, but you still have to do it yourself. So you said that the photon index is not allowed to go below 1? And this
yes, I think so.
This is a reason why this is not a good fit. Do you think, what do you think would happen if you allow photon index lower? Do you think it would be a good model?
I'm not sure, to be honest. I don't know enough about it.
Yeah, so I mean, it's difficult to judge because, I mean, this is a power law model, but you see all the detector weirdness going on. It makes the shapes complicated. But if you just imagine that slope going flatter, then it would fit maybe the high energies, but the low, this data point at 1 kV, it wouldn't be able to fit either. So it's in general not a good model because you need something that sort of turns over, that has fewer soft X-rays, lower energy X-rays. So you need something that absorbs them. And if you run the, maybe you can do that now. You ran the simplest in click, right? Maybe you can run the other scripts. So if you are in that folder, did you download? Yeah. So if you run, if you print out what's in runall.sh, it gives you all the instructions. So you just do cat, yeah, run all. So if you run Python example advanced priors, you see that line?
This one here.
Yeah, if you just do, instead of coverage run, you just do Python example one.
Like that?
Yep, exactly. So now you should get, if you make the window a bit larger, then you don't get the line breaks. Yeah, so now you see it has another parameter, which is the absorbing column density. And it's going and fitting the thing. And now it's going to be interesting to look at those plots. So now you will have hopefully a better model. And maybe you can look back what the log C value was of the power law model. Do you still have it up there? The printout, if you scroll up.
Sorry, I'm sure there's a command to jump to the top. I just don't know what it is. Is it this bit? Oh no, that's the beginning of running that.
Yeah.
This bit here.
Yes. So we had here, it said log C equals minus 3,965. And now are we looking for a higher log C value or a lower log C value? So C is the evidence. For a better model, do we want a higher evidence value or lower?
We want a higher evidence value?
Yeah. And you already see at the bottom left the logarithm of the evidence printed there. So, and it's quite a lot better, right? I mean, the other one was 3,900. This is minus 3,900 it was. This is minus 400 or so. So this is a much, much better model, regardless of what prior you would put on it.
Sorry, my computer is a bit slow. We might be waiting a while for these plots.
Well, should be almost done now.
What directory does it output into?
It should make a folder absorbed instead of simplest.
Okay.
Yeah, so now it printed out. So the log C value is higher. We would prefer this model. You see the uncertainties. You might also notice that the uncertainties are larger, for example, on the normalization. So a little bit larger because the model wasn't so bad. So it has a little bit more wiggle room to adjust to the data. And that makes a couple of plots for you. Now you should be able to find the plots in the directory. What do you think of this?
It looks like a much better fit.
Mm-hmm.
Sorry, may I also ask a question? So does it also tell us that the photon index and the hydrogen density are correlated?
Yes, so you mean so the bottom left panel?
Yes, I'm referring to the bottom left. Well, correlated. I would say that yes, in some ways. I mean.
Yes, so there are various terms for this. It's statisticians call it's non-identifiable. Astronomers usually call it a degeneracy. So if you increase the photon index, you would make the power law a bit steeper, but then you can make the absorbing column density a bit higher, then you absorb more, or you go the other way, you make it flatter and absorb less, and then both sort of fits the same data.
Okay.
Yes, there is a degeneracy there also with the normalization and the photon index. That's very strong.
Mm-hmm.
And knowing these uncertainties, these correlated, and very often they're not Gaussian like it looks here. Often they're bananas or something like that. It's very important because if you have a banana, sometimes your fit might end up on one side of the banana and sometimes on the other side of the banana. And then you might think, oh, from one object to the other object, you discover some weird trend, but it's actually just your degeneracies in the data. So it's quite important to map those out, look at them. More questions from anyone?
And when does the program usually tells us asymmetric error bars? Like, because now I see that it's just that. First of all, the error bars that it gives. So, for example, the first one, 23 plus 0.02 minus 0.02, because I suppose it's because the distribution is symmetric, right?
Mm-hmm.
It's quite symmetric, but if this wouldn't be asymmetric, then
yeah, then it would be different. So if I remember correctly, what it reports here is the mean and then the quantiles of the distribution.
Okay, so the quantiles. Okay, so automatically it should. Yeah.
Yeah, and it's very often that you get asymmetric distributions. Don't be shy, ask more questions. Well, if there are no more questions, then I will, oh, something's in the chat. What are the different colors of the data points? Yes, so this is described in the BXA documentation that you can check out. Let me just share my screen and I will point it out to you. Just so you've also seen the documentation page if you haven't. So either here or here is also a link. And then in particular, we are either in Sherpa with BXA, or how to define your priors, how to compare models, or expect with BXA. And here we are somewhere here. And then here it's described what the colors of the data points are. Essentially what I did was to try various binnings and look in each type of binning how good the data fits the model. And then I color between green, yellow, and orange. Green, yellow, and red. The quality of the fit. But usually I think you will want to do your own plotting anyways. And this is just for a quick look, convenience. This kind of plotting that's also in the simplest example. So you probably want to adjust that. Okay, so you will receive from me the slides. And yes, I wanted to point out this, yeah, and it has a couple more links. Also this longer workshop and the X-ray primer are available. If you have any questions or you're still unsure about something, there are a couple of ways to interact. I wanted to point out, well, there's an XSpec Facebook group where people ask stuff about XSpec, but also sometimes general questions about X-ray fitting. There is a Facebook group for astrostatistics that's quite active, where people ask questions and receive answers. I'm also quite active there. If you're not sure how to do some analysis or want to get feedback on a paper or something like that. And there are experts from all kinds of areas of astronomy, all kinds of analysis in there. And of course, you can email me if you have a particular specific problem that, or you have questions about BXA. If you have issues with BXA, if you find a bug, please open a GitHub issue and we can fix it that way. Okay, then I would just close by saying thanks for attending. And I enjoyed it. I hope it was useful. I hope you do awesome X-ray analysis now. And good on you for sticking with the program even in these difficult times. And all the best for your PhD. And yeah, I hope to interact with you in the future as well. I see something was...
There's a question.